Zaki va présenter ici, et donc il y a Ahmad Hably qui est a priori en ligne aussi, qui pourra aussi répondre aux questions. Et
Bonjour.
ouais, voilà. On me
Je
dit dans
suis là.
l'oreille que ça va être en anglais. J'espère que ça va aller pour vous, parce que Zaki est plus à l'aise en anglais. Et donc, en fait, on essaie de faire quelque chose un panorama, et donc c'est pas tout 100% son domaine. Elle est en thèse dans le domaine des éoliennes aéroportées, mais donc elle travaille sur un sujet particulier. Là, on essaie de faire quelque chose de global avec la Madabli. Donc, l'histoire, c'est qu'elle maîtrise pas complètement tout. Donc, c'est bien si, si tu maîtrises.
Donc, Ahmed est en ligne, effectivement. J'ai pas mis le son fort, mais s'il y a besoin de discuter, je mettrai le son.
Voilà, c'est bon.
Bonjour.
Je...
Pour français, pour la présentation. Désolée pour parler en anglais. Okay, I will switch to English. It's much easier for me. I'm Zakeye Azaki, a PhD student with Jonathan and Ahmad Hably at Gipsa-lab, University UGL in Grenoble. And I work on my PhD mainly on Earth and wind energy system, but not all over. It's only some states of or phases of Earth and wind energy system for the control approaches and this stuff. And today I will present these control issues for urban wind energy system in general. So whenever you see like wind energy, like maybe first thing that so when we see like wind energy system, the first thing that may come to our mind is the wind turbine. And this is like true. Because of that, I will begin by introducing this wind turbines. But it's not only wind turbines. There is also like technology that I will present, which is urban wind energy system. So I will talk in general, introducing this topic for you. I think not much of you know about this technology. And I will talk about some industrial work in general, very general, in this field, and some academic work, some in international or even in Gipsa-lab. Then the second part of my presentation will be on control issues for urban wind energy system in different phases, in different fields, and different concepts related to power generation, related to control issues and voltage issues. So, okay, we'll start by introducing the wind energy, introducing the wind turbine. So when we are talking about wind turbine, so this is the power produced or power available. It is related to the cubic of the wind speed available, and also it's limited by this width area, which is covered by the plate of the wind turbine. And when we have this available power, the power turbine will not produce 100%, but there is some efficiency of this, which is a limit of 59% of what we have and what is available. Okay, and then there is some work on aerodynamics and also on control aspects in order to control the wind turbines to reach and this maximum efficiency and thus to increase the efficiency of wind turbines in sense of energy production. So one thing also important to talk is the power curves. And power curves is the output power for all possible wind speeds. So whenever we have a wind speed, we have this power. And this is presented by the blue curve here. Looking also at the red curve, which is the wind distribution throughout the year, we can compute the annual energy production. And this comes to a very important factor for wind turbine, especially in economical stuff, which is the capacity factor, and it's the annual energy production over the rated power. And the rated power is this saturation limit for the power curves, which could be reached because of the power saturation for the actuators, grid connections, and grid connections. So, for example, in France in 2023, the capacity factor for all the installed onshore wind turbines was 26%. And this means that if we want to produce 1 megawatt, we have to have a wind turbine of 4 megawatts, representing the capacity factor. Okay, so looking on how we can improve the energy production of wind turbines, there is mainly two factors. The first factor is the swept area. So we can increase this swept area and then we can produce more energy. But here it comes the drawback, which is it will cost more in terms of material, in terms of mobility, in terms of costing, okay? And then we can think like, let's search for a field which has more wind. And then we can, one of the solutions, okay, let's go offshore. But also here there is complexity, especially, for example, in the floating structure that have to be added, especially when we have like a very dips in the water. So here I can conclude with some limitation of this technology related to the size. For example, here you can see how it's difficult to move the one blade of the wind turbines, and related also to the material resources, which is super important. Size availability in terms of existing wind speed. So, okay, so after presenting like what is the limitation of these wind turbines, now I will present like another solution or another technology related to wind energy, which is the urban wind energy systems. So first Lloyd in his paper, he said like this paper described a concept of for large-scale wind power production by means of aerodynamically efficient kites. Based on aircraft construction, this kites fly transfer to the wind at high speeds. Very like general for his talk is that this urban wind energy system is a kite or a flying system that is connected through a tether to the ground, and it is maneuvering in crosswind in order to generate electrical power. Must be a video there when they are working. No. Okay, so the urban wind energy system is a kite, as I've said, and it's maneuvering by figure of 8 trajectories in crosswind to generate power. So here in this phase, I am in generating power, in wind, I'm generating power. But whenever the tether reaches its maximum, it has to retrieve back. And this phase, we are using power, we are consuming power. So this is the negative power, in this phase, red, retrieving back to start figure of 8. So this is the main concept of urban wind energy systems. And this system could be classified in terms of how production is done, how energy production is done, either by track power or onboard. So we have onboard propellers generating power, and this power is transmitted to the ground via conductive cables. And then we have the lift power, which is on ground power generation. So the plane or the kite make figure of 8 due to the lift force, the big lift force. It can also make a traction force from the tether, and this traction force leads to a mechanical movement which can generate electricity but on ground. In terms of kites, we can have like soft kites or rich kites and propellers, and here comes more the robotic fleets and drones and this stuff. And we have also the onboard with propellers inboard to generate electricity, as I've said, onboard and then transmitted to the ground. So one important aspect for everyone energy system, similar to the wind turbine, it is the efficiency, or here it is the power harvesting factor seen here. So in order to have like a reasonable factor for power generation, which is maybe like around 40, 50, 60, we have to make this crosswind figure of 8 trajectories in Earth. And thus here comes the control part problem. Okay, we have to control this system to make this figure of 8 like trajectory tracking to generate this good power production. Also, for example, when we are saying that we have a kite flying in the wind, so we can imagine that, okay, it can reach higher and higher altitudes. So, for example, wind turbines, conventional wind turbines, it is like around 100 meters, and for the edge of the plate, it could be like 150 meters. But for every wind energy system, we can reach 400 meters, around 400 meters. And in this case, there is, in these altitudes, maybe we have higher wind and more consistent wind in order to produce energy from this wind. So this is an advantage and good advantage for every wind energy system. Talking about materials used and footprint, so for sure we can imagine now that, okay, the tower and foundation of the wind turbine, we are getting rid of this, and this is like a big amount of materials. Also in terms of plates, now we may have smaller plates, okay, but still this is like a theoretical analysis done by a startup in Archive, and but just there must be more real work in order to have this general view about materials. For example, there is not on the on-ground container or on-ground station that it may have a lot of material, it may use a lot of materials, metals and stuff. There is also the maintenance of changing parts or changing the tethers. Anybody? Okay, so to conclude on this part, comparison between wind turbines and wind energy system limitations and advantages, we can say that, okay, a wind energy system can reach higher altitudes, so more consistent wind, more wind, and by using less material, but still it is very complex to control, to design, and so we have to, it requires a reliable and robust control in this stage. So here we are talking more on the complexity of this system. And also it depends on high performance materials like feather metals. Okay, very, very briefly, I will present some work done in this wind energy system, not work, but systems. So here it's, there is startup, which is the simpler but most advanced for this technology. Here you can see that it is soft parts, everything is soft parts. Here is the on-ground containers or on-ground stations. And the sky says is will be in the process to be the first commercial technology for about 100 kilowatts. Here there is the fixed or rigid kites, so more with propellers and fixed twin kites. But I want to set the light on the wind picture, the one here, so you can see that there is some magnets, some cylinders, and this is our magnet cylinders, which may generate power because of the rotation. So it generates lift power if there is wind. And this is a French startup that our lab, Gipsa-lab, is collaborating with. Here is some complex configurations. Mechanical power has been lost and the kite craft. Also here it is kind applications for sales. So mentioning the French companies beyond the sea and air seas. Okay, this is the picture during the Urban Energy System Conference in Milan in 2021. Maybe we don't have time to search the searching game for me and Jonathan. Maybe you are here as well. I can see myself, but you are here. And this is the map. It was before 2023 for companies, for startups, and academia working on it. And here, for example, we have Grenoble-INP, our university. Okay, so I will come now to the second part of this presentation, which is the control issue for urban energy system. I don't have to be more interested in this concept. So talking about this, I will go to different aspects, different groups and phases. So first talking about modeling and the system itself. So we have first the on-ground, which is the simplest in this system because it can be controlled by classical for control, but we have state saturation, friction, uncertainties in measurements. Then we have this tether, which is not easy to model. Its modeling is based on multiple models. And so if we don't have a good model for the tether, we will not be able to simulate or we will not be able to study the effect of this tether's drag, for example, on the performance of the aircraft. And also talking about the kite itself, all the actuators for this flight system have an aerodynamic characteristic, even if it's the wings or even if there is some propellers producing some aerodynamic disturbances. And these models are not really reliable and it's complex to have this model. And since the control, the analysis of and study of this system is based on this model, so this is somehow like a problem or a limitation. And there must be more work on this area. Also, this aerodynamic, it is for sure they depend on the apparent or relative airspeed. So we have the wind speed in one case that we must have a reliable wind sensor. And also we have the speed of the flight, which could be measured by GPS or whatever, but we still have like a complexity and delay issues in communication. So this is also some limitations. Then we have, in order to do this figure of 842, we have to do some trajectory tracking controller. So I will not go into this, just with there is some cascade control loop that will be used in order to generate.
Ah, les gens sont là. Tu peux peut-être partager ton écran.
Bon, c'est toutes les semaines.
Ouais, bon, c'est pas le problème. Là,
Non, c'est pas le problème. Ça a coupé.
C'est bon.
Okay, and then a higher level for the control is how to optimize the energy production through the control. So this was a work done at Gipsa-lab, our lab. So for a defined figure of 8, how to adapt this trajectory in order to, in sense of optimizing the energy produced. There is also work done by maître Gipsa-lab that is working also on how to optimize the energy production, but not only during the traction phase or during the production phase, but also during the whole cycle, which is production phase on one hand, and also the retraction, which consume energy on the other hand. And the results shown in bold for the power that, okay, we optimize in terms of the full cycle, we can have better performance in terms of power compared to if only we optimize during the traction or during the production phase. Also, this work was done at Gipsa-lab, which show that the power produced by urban energy system can be controlled. For example, we can imagine a scenario where we have a lot of wind and we are not using this all wind. So in that case, we may have negative powers, and for that we can control how much power we can produce from urban energy system, so not to reach its maximum power that can produce, but the power that we need. And this is done by controlling the interaction of the tether source in another way, in another meaning, like controlling the production of the urban energy system. Also, some work at Gipsa-lab was done on power curves of urban energy system. I will not talk about too much. And for the classical wind turbines, and they have the same trend in such a way that it's reaching a certain rate power because of power saturation, because of grid connections.
Sorry, the screen is not sharing anymore. But it's working, so I don't know. Ouais.
Okay. Now, the last topic for this presentation is the takeoff and landing phases. So for wind turbines, for sure, we don't have this issue. We don't have to take off or land, for sure. But for urban wind energy system, we have to. And this is our critical phases in urban wind energy system, especially if we have wind conditions, disturbing wind conditions. And mainly this is my objective, my PhD objective, to control urban wind energy system during takeoff and landing phases. So I will present some academic work on this topic, different academic work, using different approaches to take off and land, using different control, using different systems. So in order to compare this takeoff and landing strategies, there is some quantitative and qualitative criteria. So first it is looking at the additional power installed. So if we want some propellers, additional propellers to take off, this is additional onboard power and additional onboard mass as well. Looking also to the ground area occupied for the takeoff and landing, how much area we should have to take off and land. Using also the complexity and cost of the components needed to be added. Also, lastly, it is the capability to take off and land under different wind conditions or even under for no wind conditions. So this work was done at Politecnico Milano, and it is using a system of fixed wing with a propeller, horizontal propeller. It's connected to a rail. So this rail will accelerate the aircraft until it reaches a certain speed that can make it lift, and then it climbs up to the needed or required altitude. This was tested outdoors for wind between 0 and 5 meters per second. Another approach for the takeoff and landing was used by University of takeoff. For example, it will pass by different phases. At each phase, there is the on reference, the on control strategy, and the main control strategy was using the PID and FUR. Also at QLevant, they used also the same approach, which is the circular taking off, But in this case, the kite will be connected to a rotating arm. So this rotating arm will rotate, accelerating the kite, and whenever it reaches to the enough speed, it will be disattached and then it will fly to the altitude. Our plan on Polytechnical of Milan was to take off and land like vertical takeoff and landing, but the system was this boxed wing drone. It was controlled by Cascade PID controllers, and it was tested in simulation, but it is no wind speeds. There is a work in Aachen University is talking about this complex structure, which is a vertical fixed wing with propellers. And mainly the most critical part here is how to control the pitching of the system. So they reach that for a certain low speed between 5 and 10 meters per second, they will not be able to do this pitching control. And so they proposed some design approaches in order to improve this critical situations. Coming to our work at Gipsa-lab, so our work at Gipsa-lab is also concerning vertical takeoff and landing, but using a feedback linearization control, which is to compensate some non-linearities in the model of the system. And also we are using a sliding mode control, which is used in order to be more accurate in terms of power wind disturbances, to be more robust against them. So, for example, in my PhD, we are working on this system. This system is composed of a quadcopter, and we have these two cylinders. It's the magnet cylinder. So here we have, as if we have two actuators, which are the quadcopter at one hand, and we also have the two magnets at the other hand that generate lift and drag to be used in controlling or in takeoff and landing. So in this case, we are using an optimization-based control allocation strategy in order to allocate the contribution, the force contribution between the quadcopter and the two magnet cylinders. So here, the wind is not considered as a disturbance during the takeoff and landing, but also it's considered as a source of lifting for the takeoff and landing. So we can reach higher wind speeds, fly or takeoff and land for higher wind speeds, and also we can reduce the power generated or the power consumed by the quadcopter to take off and land, because now we have the magnets helping it. So this is a video of takeoff and landing, under 4 meters per second. We can see how critical the landing is for such system. We have wind turbines which produce in very turbulent wind speeds. And now for 6 meters per second, we crash, and then we take it manually. And this is because of some saturation of the actuators, because of some aerodynamic momentums. Lastly, also at Gipsa-lab, we are proposing a strategy of estimating this lift and drag forces for wind energy system based. So, for example, here in this figure, we can see the lift and drag option in blue, dots or stars is estimated, and in red is the motor, and we see like a good fitting between both. And for a conclusion, so I presented the airborne wind energy system, which is a promising in terms of energy system production, but also still a very complex technology. So further studies are needed to realize the full potential of it. None of the projects has proven more than a few days of operation. For the automation of the system, we have to think about to automate the full cycle of the system. So the takeoff, the landing, the power generation, the retrieval phase, and also the interference between them. We have to deal with some regulations, for example, interference with air, traffic and ground use in case of radar, for example. Also, we have to think about durability of materials to sustain a high number of load cycles, since critical components like tether and kites are used, and look for reliability and safety of the system. Ok, j'ai fini en français. C'est tout et merci.
Merci. Des questions, tu peux voir pour récupérer le drive. Ouais, j'ai renvoyé à Jonathan. Merci. Donc, vous avez des questions? Ouais, Laura?
Thank you very much for the presentation. I didn't know about this approach. Interesting. Do you think that it has the potential to be better than the classical windmills? And is it more ecological? Yes.
Yeah, now it's like they are not like a competitive technology. They have to be together in a sense. And there must be like, it's like a technology which is not fully studied for now, like water turbines, it's really studied for many years. And so I think it has to take more time in order to analyze the study. For now, there is no commercial technology or system for urban wind energy system. So yes, I think we cannot say like we have to get rid of wind turbines or rely only on this urban wind energy system for now, because they are like we can use solar energy, we can use wind turbines.
Because if you're like one of the first slides where you compare both, it seems that all the quantities that were positive were actually attributed to the wind turbines.
No, it was wind. It was quality of airborne energy.
Yeah. The positive and the negative were both for urban wind energy systems. So I was looking on
okay, that's why.
Yeah.
C'était perturbant parce que c'était au-dessus de l'éolienne, mais en fait, c'était juste la comparaison.
Yeah, so if you're interested, so this is something that can do a transition from mechanical to electrical. Maybe also in water.
In
water.
In water, like
On peut parler en français hein, pour les questions.
Oui,
c'est un lien drive. Oui. Si vous pouvez parler fort pour que Ahmed puisse entendre et éventuellement intervenir. Peut-être pas répéter, mais au moins ce qu'on dit maintenant.
I understand if we can use it more for underwater, electrical.
Underwater to transform mechanical energy
to the electrical.
Or turbines are
je peux répondre à...
Vous m'entendez? Il y a des gens qui ont essayé de faire des choses comme ça en sous-marin, mais
oui.
Le problème, c'est encore plus compliqué parce que c'est sous l'eau. Après, il n'y a pas le problème de décollage-atterrissage parce que c'est dans l'eau. Ouais. Mais c'est des choses qui sont potentiellement faisables. Après, il n'y a pas de communauté comme pour l'aérien.
Elle y a toujours... Vous m'entendez?
Oui.
Oui, en fait, il y a un groupe qui travaille sur les cerfs-volants sous-marins. Mais en fait, le problème, c'est en plus de décollage, atterrissage, en fait, il y a le problème de localisation de ce type de système, parce qu'il faut mettre des types de radars pour localiser. C'est pas juste avec la mesure de tension dans le câble, on peut localiser la partie dynamique. Et ça pose un vrai problème de comment mettre. Donc c'est peut-être, c'est pas pour l'énergie, peut-être pour d'autres applications, on peut dire militaires, peut-être ils peuvent l'utiliser, mais pour l'énergie, c'est un petit peu compliqué ce type d'application.
Une petite anecdote rigolote quand même, c'est que à l'époque où on mettait beaucoup de moulins à eau sur les rivières, donc il y avait
Oui,
on utilise beaucoup ça. Et en fait, il y a toute une gamme de moulins flottants qui existaient. Donc c'était sur des bateaux avec des roues à eau. En fait, ça revient un peu à la même idée, c'est-à-dire qu'en fait, on avait des roues à eau, des moulins qui étaient fluctuants, qui étaient attachés à un câble sur le bras et qui pouvaient fluctuer comme ça. Et donc finalement, à cette époque-là, on avait déjà quelque chose au bout d'un câble qui s'adaptait au niveau de l'eau, notamment parce que quand il y avait des crues ou des choses comme ça, c'était intéressant. Il y avait tout un tas de micro-usines qui flottaient sur les cours d'eau, en fait.
Et là, l'avantage aussi, c'est l'impact visuel, j'imagine que ça, c'est pas mal, ouais.
Une question un peu au hasard, mais c'est quand le truc est en haut, il faut tirer, ça coûte de l'énergie. Mais il y a la gravité. Donc, ce qu'on pourrait faire imaginer, donc, là, le dispositif qui sont en bout et ça tombe, et dit pour faire de l'énergie, plutôt que de faire de l'énergie, parce que tirer un câble qui est pas tendu, ça coûte rien comme énergie.
Yeah, because this, I don't know if I understand, but this power for the retrieval of the aircraft, it is not too much compared to what is produced. But I don't know if you are talking about gravity to
Yes.
take it back, just like Paul, yeah. Yes, it was the proposition for an engineer at Gipsa-lab.
Non, non, non. En fin de compte, la production, on va dire, c'est ça, et la consommation, c'est ça. Et donc, finalement, on pourrait dire, bah, je consomme ça, donc je pourrais consommer, comme tu dis, on pourrait ne rien consommer. Ça serait complexe à faire, mais pourquoi pas? En fait, le vrai problème, c'est que c'est plutôt qu'on consomme pas, on produit pas pendant ce temps-là. C'est l'énergie perdue pendant ce temps. Et c'est plutôt ça, en fait, qui fait qu'on perd en efficacité. C'est plutôt l'enjeu est plutôt sur le temps de retour que sur l'énergie consommée à ce moment-là. Parce que pendant ce temps-là,
Ça épuise, quoi.
voilà.
Donc, ça revient
C'est ça.
que la gravité.
Voilà. En fin de compte, on a plutôt intérêt, quand on regarde le cycle dans sa globalité, à réduire au maximum ce temps-là, parce que pendant tout ce temps-là, ma machine, elle est là, mais elle ne produit pas. Alors qu'il y a du vent, donc je laisse passer le vent, en fait. Donc c'est un peu le bon. Ouais.
Bon. D'autres questions? Très bien, merci. Merci beaucoup. Ah, et c'est pas grave, hein, c'est bien.
merci.
Merci à vous.
Voilà.